In the realm of tool-layer neural networks, the geometry of the loss landscape near global minima remains a crucial aspect to explore, particularly in the context of overparameterization. This paper delves into this topic, revealing that global minima with zero generalization error become geometrically separated as the sample size increases. This separation is attributed to the emergence of multiple, isolated minima, each corresponding to a distinct set of neural network parameters. The authors employ novel techniques to analyze the local convergence properties and rate of gradient flow dynamics. By leveraging linear independence of neurons, the theory of real analytic functions, and the geometry of Q, they demonstrate that tool-layer neural networks can be locally recovered in the regime of overparameterization. This means that, despite the abundance of parameters, the network can still converge to a global minimum, albeit with a unique set of parameters. The findings of this research have significant implications for our understanding of neural network behavior near global minima. By shedding light on the geometry of the loss landscape, this study provides valuable insights into the mechanisms underlying neural network optimization. Furthermore, the novel techniques employed in this research pave the way for future investigations into the intricacies of neural network optimization, particularly in the context of overparameterization. Neural networks are a cornerstone of artificial intelligence, yet their mathematical underpinnings remain poorly understood. The loss landscape of neural networks, particularly the geometry of global minima, significantly influences their training dynamics and generalization capabilities. This paper delves into the geometric structure and local recovery problem for tool-layer neural networks, focusing on perfect global minima that accurately recover the target function. The authors reveal that this set consists of distinct branches that diverge from imperfect global minima as the network becomes overparameterized, ensuring local recovery capability and reducing the difficulty in finding well-generalizing solutions. The geometry near different branches exhibits distinct limiting behavior of gradient flows, inherently tied to the neural network model family. This research demonstrates the profound impact of the fine geometry of global minima on neural network generalization, contrasting with traditional machine learning problems where global minima have trivial geometry. It highlights the importance of analyzing the geometry of the well-generalizing set, particularly the perfect global minima, within the global minima of the loss landscape to understand generalization. The study refines the view suggested by Cooper, which focuses on the overall geometry of global minima. The authors emphasize that the global minima or critical points of the loss landscape possess rich geometric structures that are amenable to analysis, mathematically interesting, and intrinsic to the model architecture, playing a fundamental role in exceptional training and generalization performance. The study of global minima in the loss landscape presents two fundamental issues: the linear independence of neurons and their derivatives, which determines geometric structures of the loss landscape, such as dimensions of global minima. The research on this page delves into understanding the separation between perfect and imperfect global minima in neural networks. It establishes the linear independence of neurons and their derivatives to address the issue of highly degenerate Hessians at global minima. Traditional methods are insufficient due to the loss not being a Morse function. The study devises methods for analyzing gradient flow dynamics near degenerate critical points, broadening the scope of existing research. The approach involves presenting main results informally, followed by proofs, and then detailed treatments of geometry and functional properties. The convergence rates and directions of gradient flows near perfect global minima are investigated, leading to unprecedented results. This paper offers a comprehensive overview of theoretical results and their interconnections, as illustrated in Figure 1. The main components are presented in dark pink boxes, with fundamental theories outlined in green boxes and other findings in yellow boxes. Notably, the paper employs n to represent the set of natural numbers, 1, 2, 3. For any two elements x, y within a Hilbert space, the inner product is denoted by x, y or x, y. The gradient of a function f is denoted as nabla f, while the Hessian of f is represented as Hess f. In the context of a Hilbert space, the closure of a subset E is denoted by E. A subset E is said to have lambda k measure 0 if its k-dimensional Lebesgue measure is well defined and equal to 0. This paper explores a generic collection of analytic activations, which yields a reasonable linear independence result. These analytic activations, denoted by sigma, r right pointing arrow r, must satisfy specific conditions, including infinite differentiability and a non-zero radius of convergence. The exponential activation is a prime example of such a generic activation, whereas sigmoid and tanh activations do not meet these requirements. The motivation behind these activations is to preserve the number of first-layer features, ensuring that neurons act as effective feature maps. The paper's core result, Proposition 3.1, demonstrates that when distinct weights are employed, the corresponding activations are linearly independent. This linear independence is a crucial property, as it enables the network to learn diverse and meaningful representations. The implications of this finding are far-reaching, with significant potential to improve the performance and robustness of neural networks in various applications. We investigate the approximation capabilities of two-layer neural networks, focusing on a model G that maps from the parameter space X and input space R⁻D to R. Specifically, we consider a two-layer neural network with an activation function sigma, where G, theta, X, equals sigma⁻m_1 a_k sigma, W_kx. For theta element of R⁻D plus 1, m and X element of R⁻D. The target function f is a two-layer neural network with m_0 features, defined as f, x, equals sigma⁻m_0_1 a_k sigma, W_kx. We denote the collection of such models as G_m, which is a subset of the larger collection G. The empirical L2 loss function R measures the difference between the model's output and the target function over the input space R⁻D. In the finite feature setting, the target function f has a finite number of features, and the collection of models G_m includes models with at least as many features as f. The loss function R, theta, is given by the sum of squared differences between the model's predictions and the target function's values at n distinct input points x_i equals 1, n. In the context of overparameterized neural networks, the local recovery problem arises, where the challenge is to ensure that the network can perfectly recover the target function with zero generalization error in a local region of its parameter space. This problem is attributed to the complex, non-convex nature of the loss landscape, featuring infinitely many global minima that form intricate patterns. The local recovery problem encompasses three key aspects: geometric structure, separation of minima, and convergent gradient dynamics. Geometric structure involves investigating the recovery of the target function, focusing on the geometry of global minima and the relation between sample size and global minima geometry. Separation of minima refers to the possibility that perfect global minima, which accurately recover the target function, can become separated from other global minima, ensuring the model recovers the target function. Convergent gradient dynamics involve understanding the limiting properties of gradient-based optimization methods near these minima, essential for efficient training. The perfect global minima set Q** operator is defined as the set of parameters theta element of R, D plus 1, m such that G, theta, equals F** operator. Notably, Q** operator subset equal R-1, 0, and R-1, 0, Q** operator is referred to as imperfect global minima. In overparameterized models, where micro equals Pni equals 1 delta, minus xi, with n is less than or equal to d plus 1, m, analysis becomes challenging. In contrast, underparameterized models, where micro equals rho dx for some continuous function rho right pointing arrow, 0, plus infinity, are more tractable. The gradient flow gamma is defined as gamma equals, ac, weak, mk equals 1, 0, plus infinity, right pointing arrow r, d plus 1, m with initial value theta 0 equals, ac, 0, weak, 0, mk equals 1 element of r, d plus 1, m. The gradient flow is characterized by gamma t equals ac t weak t mk equals 1 equals minus sign nabla r, gamma t gamma 0 equals theta 0. Specifically, when r has the form in equation 2, we have for k equals 1, m, ac t equals minus sign partial differential r partial differential ac gamma t equals 2 n sigma I equals 1 g gamma t xi minus f asterisk operator xi sigma weak t xi and weak t equals minus sign partial differential r partial differential weak gamma t equals 2 ac t n sigma I equals 1 g gamma t xi minus f asterisk operator xi sigma weak t xi. The local recovery problem, introduced by the authors, seeks to understand how geometric and dynamic properties of the loss landscape influence a neural network's ability to identify and utilize perfect generalizing solutions during training. This problem involves developing strategies to navigate the complex loss landscape and comprehend why the network can effectively recover the target function in local regions. To illustrate this problem, the authors consider a specific example of a twineuron model with an exponential activation function and unidimensional input. The loss function, r, theta, is defined as the sum of squared differences between the model's output and the target output. By applying Cooper's results, the authors show that the zero set of r 1, 0, is a submanifold of r 6 with dimension max 0, 6n. The authors then consider the case where the target function, f, is expressible by the given two-layer neural network, allowing for perfect generalization. They uncover a more detailed structure of the global minima of R, illustrating it with a simple example where f x equals a wx. The loss function is rewritten as r theta equals underscore I equals 1 n g theta x underscore I a wx underscore I squared. The authors observe that w1x and w2x are linearly independent if and only if w1 does not equal w2. Based on the number of distinct w_k's, they partition the perfect global minima into three sets, Q1, Q2, and Q3, which are independent of the training inputs. These sets, Q1, Q2, and Q3, geometrically resemble three branches with different dimensions, as shown in the figure. The author's analysis provides insight into the structure of the global minima of the loss function, highlighting the importance of understanding the geometric and dynamic properties of the loss landscape in addressing the local recovery problem. Figure 2 illustrates the concept of Q** operator, which is composed of the closure of branches Q1, Q2, and Q3. These branches are affine subspaces in the parameter space, with Q1 and Q2 intersecting at a, w, 0, w, and Q1 and Q3 intersecting at 0, w, a, w. In the context of neural networks, when the sample size n is greater than or equal to 6, the network achieves perfect generalization when it converges to zero loss, with no imperfect global minima. However, when the sample size is less than 6, imperfect global minima generally exist, raising questions about the relationship between perfect global minima and imperfect global minima. To understand perfect generalization in two-layer neural networks, three key questions must be addressed. Firstly, what is the geometric structure of the perfect global minima Q** operator? Secondly, how is Q** operator related to the imperfect global minima r-1, 0? Q** operator, and can it be separated from them? Lastly, what are the convergence dynamics of gradient flows near r-1, 0, including convergence rates, directions, and stability? Previous work by Simcik and Fukumizu has already provided insight into the geometric structure of Q** operator, showing that it is a set with symmetry and comprises the union of finitely many branches of different dimensions, each with an affine subspace closure. Building on this understanding, sections 4 and 5 provide detailed answers to the latter two questions, while section 2.3 presents informal theorems summarizing the results. These theorems are then applied to the example presented in Figure 2. The primary findings of this research are encapsulated in the form of theorems, which elucidate the local recovery of two-layer neural networks. Theorem 2.1 establishes the separation of branches in Q** operator, where each branch Qt corresponds to a sample size threshold ent is less than or equal to m, d plus 1. This theorem states that when the sample size n is greater than or equal to ent, Qt is separated from the imperfect global minima. Moreover, it provides a partition of Q** operator into two parts. Qt for t is less than or equal to n and Qt for t greater than n, where Qt is not Morse-bot anywhere for t is less than or equal to n and Morse-bot almost everywhere for t greater than n. The separation of Qt is defined as the existence of an open set U subset equal R, d plus 1, m such that U intersection R caret 1, 0, equals U intersection Qt. The Morse-bot function f is defined as a function with a non-degenerate Hessian along the normal bundle of a manifold in nabla f, caret 1, 0. The proof of Theorem 2.1 relies on the theory of real analytic functions presented in section 3.2 and is detailed in lemmas 4.2 and 4.3 in section 4. Theorem 2.2 characterizes the behavior of gradient flows near R caret 1, 0. Specifically, it states that any gradient flow sufficiently close to R caret 1, 0 converges, and any point in R caret 1, 0 is the limit of some gradient flow. The theorem further provides two scenarios. For t is less than or equal to n and sample size n is greater than or equal to ent, a generic gradient flow sufficiently close to Qt converges to a point theta element of Qt, and for t greater than n and sample size n is greater than or equal to ent, any gradient flow sufficiently close to Qt converges to Qt at a linear rate. The results of theorems 2.1 and 2.2 comprehensively exhibit the structural change of geometry and local dynamics of global minima at the overparameterized regime, with the perfect global minima Q** operator as its backbone. The branch separation and convergence results guarantee the local recovery capability of two-layer neural networks, i.e., the target function will be recovered when initialized near separated branches. The results also suggest a mechanism of generalization at overparameterization, where proper generic initialization in hyperparameter tuning can guide the gradient dynamics to a neighborhood of the separated branches of Q** operator, thus recovering the target function at convergence. The section on page 11 of the research paper continues to explore the twineuron model, applying theorems 2.1 and 2.2 to investigate local recovery theorems. Specifically, it is demonstrated that the set Q** operator, comprising three subsets of R to the power of 4, can be characterized as a union of affine subspaces. The subset Q is unidimensional, while Q and Q are two-dimensional minus a point, aligning with the observation and figure 2. Each subset Qt, 1 is less than or equal to t is less than or equal to 3, corresponds to a sample size ent, making it separated, with n equals 5 and n equals 4. Theorem 2.1 indicates that the loss function R is not Morse-bot anywhere at Qt if t equals 1, and R is Morse-bot almost everywhere at Qt if t equals 2, 3. Theorem 2.2 is then applied to show that any gradient flow sufficiently near R, 0, converges to it, and any point in R, 0, is the limit of some gradient flow. This implies that a generic gradient flow gamma does not converge to a point theta asterisk operator element of Q at a linear rate and is biased towards Kerr-Hess R, theta asterisk operator, when the sample size n is greater than or equal to 5. However, any gradient flow gamma converging to a point in QQ has a linear rate when n is greater than or equal to 4. Figure 3 illustrates these properties of Q** operator and gradient flow nearby, showcasing the characteristics of Q** operator and the behavior of gradient flows in the vicinity of Q, Q, and Q. The section then transitions to preparing lemmas and propositions for the proof of the main results, starting with the linear independence of neurons with a generic activation. The concept of separating inputs is introduced, defined in definition 3.1, and the choice of samples affecting the rank of certain matrices is discussed. Basic results about the zero set of real analytic functions are presented, some of which will be used in section 3.3. The page then summarizes and rephrases the results about the geometry of Q given by B. Simsek, K. Fukumizu. The main result is lemma 3.1, which characterizes epsilon polynomial. It states that for any m, L element of n and distinct P1, PR element of R, 0, the power series in epsilon is a polynomial if and only if alpha tk equals 0 for all 1 is less than or equal to t is less than or equal to L and 1 is less than or equal to k is less than or equal to R. This is proven through two cases. A. P1 greater than P2, and B. P1 equals P2. The lemma's implications on the properties of the power series and its relationship with the separating inputs are crucial for understanding the paper's main arguments. In this section, the authors delve into the linear independence of neurons in a neural network, introducing corollary 3.1. This corollary states that a real analytic function sigma R right-pointing arrow R is a generic activation if and only if for any R greater than 0 in distinct vectors W1, WR element of road, the functions sigma, W1x, sigma, WRx, are linearly independent. The proof begins by assuming that sigma is a generic activation. It then shows that for any R greater than 0 in distinct vectors W1, WR element of road, there exists an E element of partial differential B, 0, 1, such that pk equals open angle bracket weak, E close angle bracket does not equal open angle bracket wj, E close angle bracket for k does not equal j. This implies that x rightwards arrow from bar prk equals 1 alpha k sigma, weak x, is a zero map, leading to a series of equations that eventually result in alpha 1 equals alpha r equals 0. Thus, sigma, w1x, sigma, wrx, are linearly independent. Conversely, if sigma is not a generic activation, it can be shown that for any r greater than 2, n plus 1, d, the function sigma, w1x, sigma, w1x, sigma, wrx, sigma, wrx, cannot be linearly independent. Similarly, if sigma is not a generic activation, for sufficiently large r, the function sigma, w1x, sigma, w1x, sigma, wrx, sigma, wrx, cannot be linearly independent. This section emphasizes the significance of linear independence in neural networks and provides a detailed analysis of its relationship with generic activations. The results presented here have implications for understanding the capacity and expressiveness of neural networks. The current analysis of loss landscapes for neural networks focuses on polynomial and non-polynomial activations separately. However, this research proves the linear independence of neurons for analytic activations, which is a significant contribution. The proof of proposition 3.1 shows that if the activation function is analytic and not a polynomial, then the outputs of the neurons are linearly independent. This result holds for specific activation functions like sigmoid, hyperbolic tangent, and the logarithmic function. The analysis also considers other important properties of activation functions, such as rapid decreasing and non-asymptotic symmetry, which are crucial for neuron independence. Examples of activation functions satisfying these properties are provided, including exponential functions. This work expands our understanding of neuron independence, particularly for analytic and non-polynomial activations, offering insights into the behavior of neural networks. The authors discuss the properties of sigmoid functions sigma, x, and their derivatives, focusing on three specific cases. In the first case, sigma, x, equals 1 plus e caret, x, with s equals 1. The derivative of sigma, x, decreases rapidly as x approaches infinity. Specifically, lim x right pointing arrow plus minus infinity sign sigma, x, equals e caret, x, 1 plus e caret, x, squared. This property is essential for the subsequent proofs. The second case involves sigma, x, equals log 1 plus e caret x, with s equals 2. And the third case is sigma, x, equals tan h, x, both of which also decrease rapidly. The authors highlight that these sigmoid functions do not satisfy the non-asymptotic symmetry property. However, by horizontally shifting the sigmoid function by b element of R, namely, sigma, xb, the authors obtain a function that satisfies both the rapid decreasing property and the non-asymptotic symmetry property. The authors then present proposition 3.1, which states that if sigma satisfies assumption 3.1, then the function sigma w1x sigma w underscore rx are linearly independent for distinct vectors w1 w underscore r element of r caret d 0. The proof involves constructing a zero map G epsilon and analyzing its STH derivative, showing that the constants alpha 1 alpha underscore r must be 0, implying the linear independence of the functions. The passage discusses the linear independence of neurons in a neural network, starting with the premise that if p1 equals p2, then p1 equals minus p2 and p1 equals p2 greater than pk for all k does not equal 1, 2. This leads to the conclusion that for a specific function gs epsilon, it can be rewritten using p1 equals minus p2. The non-asymptotic symmetry property of the function sigma s is then used to derive bounds for alpha 1, ultimately showing that alpha 1 equals 0. The linear independence of the neurons is established by repeating this argument. The discussion highlights the importance of the symmetry property of sigma s in dealing with cases where pk equals minus pj for some k, j. The result holds for various commonly seen neurons, including sigmoid, hyperbolic tangent, and exponential functions. In neural networks, the properties of the generic activation function sigma play a crucial role in separating inputs and determining the rank of related matrices. Two propositions demonstrate how distinct inputs can be distinguished based on their behaviors, even when they are close. Proposition 3.1 shows that the activation function is continuous, allowing it to differentiate between inputs with a certain level of precision. Specifically, for any epsilon greater than 0, there exists a delta greater than 0 such that if xy less than delta, then sigma x sigma y greater than epsilon. This continuity ensures that the activation function can capture subtle differences between inputs. The second proposition addresses the asymptotic behavior of the activation function at infinity, stating that for any epsilon greater than 0, there exists an r greater than 0 such that if x greater than r, then sigma x greater than epsilon. This implies that the activation function exhibits non-vanishing behavior as input values approach infinity. A corollary considers a matrix composed of rows of vectors v, sigma, where v, sigma equals sigma w1 xi, sigma wm xi, sigma w1 xi xti, sigma wm xi xti. The corollary proves that for any r in n and distinct w1, wr element of road, there exist x1, x, d plus 1, r such that the matrix has full rank. This result is essential for understanding the expressiveness of neural networks and their ability to approximate complex functions. The proof of the corollary employs induction, first considering the case r equals 1, where x1 is chosen not orthogonal to w1, ensuring sigma w1 x1 is non-zero. For r greater than 1, an east element of road is selected satisfying certain conditions, and a similar matrix with r1 rows is considered. By carefully choosing E, the map defined by the matrix is shown to be non-zero, implying the matrix has rank r. This, in turn, implies that the original matrix with r rows also has rank r. These results have significant implications for neural networks and their approximation capabilities. The choice of activation function is crucial in determining the network's performance, and different activation functions can lead to distinct behaviors in the network. The proof of proposition 3.1 is extended to show that for any $e in math bb r caret d satisfying $p underscore k nec p underscore j for $k nec j, there exists a perturbed $e such that the analytic function epsilon mapsto sum underscore k equals 1 caret rb underscore 0 caret k sigma epsilon p underscore k plus sum underscore k equals 1 caret r langle b underscore 1 caret k e rangle sigma epsilon p underscore k epsilon is not a zero map. This result inspires the definition of separating inputs. Separating inputs are defined as a set of $n inputs $x underscore I underscore I equals 1, caret n dollar such that the matrix in equation 7 has full rank. The existence of separating inputs for any dollar theta equals a underscore k, w underscore k, underscore k equals 1, caret m, in math bb, r, caret d plus 1, m, dollar is guaranteed by corollary 3.2. The theory of real analytic functions is introduced, including the analytic implicit function theorem, lemma 3.2. This theorem states that for a smooth map $f, m underscore 1 to m underscore 2 dollars with constant rank $s dollar, there exist analytic coordinate maps $phi dollar and $psi dollar such that equation 8 holds. This result is used to analyze the geometry of the loss landscape of $r near its global minima. The section discusses lemma 3.3, focusing on the properties of analytic functions and their zero sets. It begins by stating that for any connected open set omega and an analytic function f, omega right pointing arrow r, either f equals 0 on omega or f minus 1, 0, has lambda, d plus 1, m measure 0. This means the zero set of the function either covers the entire set or has measure 0. The lemma then explores the properties of f-1, 0, particularly when f is not a zero map. It asserts that for any point z0 in the zero set, the set can be locally contained in a finite union of analytic smooth manifolds of dimension d plus 1, m-1. The proof involves an induction on the dimension of the space and utilizes the properties of analytic functions to demonstrate that the zero set has measure 0. This lemma is crucial for understanding the behavior of analytic functions and their zero sets in the context of the paper's main arguments. In high-dimensional spaces, the intersection of two manifolds, M1 and M2, is examined. A fundamental contradiction arises when considering a point x in the intersection of M1 and M2, as it must also lie in the closure of M2, leading to the conclusion that there is no common point between the two manifolds. In the context of analytic functions, a crucial result is established. Given an analytic function f that is not constantly 0, for any prescribed points, a perturbation can be found such that the set of common zeros of f is empty. This finding has significant implications for controlling the size of the global minimum of a function, as it provides a means to manipulate the zeros of the function to achieve a desired minimum. The technique outlined here is critical in controlling the global minimum, as it offers a way to perturb the points to avoid common zeros, thereby influencing the minimum value of the function. This approach has far-reaching implications for optimization problems, where understanding the behavior of the global minimum is essential. Separating inputs and their properties is a fundamental concept in this research. A key result, corollary 3.5, establishes that under certain assumptions, separating inputs exist almost everywhere. This is proven by constructing a matrix A from the inputs and weights, which has a non-zero determinant for an open dense subset of the weight space. This implies that the inputs are separating for almost all choices of weights, a crucial property for many applications. The geometry of Q** operator is then examined, focusing on the global minima of the loss function and the connectivity of Q** operator. To understand the intersections of different branches of Q** operator, the concepts of partition and refinement are introduced. The goal is to partition Q** operator into symmetric subsets based on the number of distinct weights, a crucial step for local recovery. This partitioning enables a deeper understanding of the structure of Q** operator, allowing for more effective optimization and recovery techniques. By establishing the existence of separating inputs and characterizing the geometry of Q** operator, this research provides a solid foundation for further exploration of these concepts and their applications. The implications of these results have the potential to significantly impact various fields, including machine learning and data analysis. The research paper discusses the fragmentation and stratification of Q** operator, a key concept in machine learning and artificial intelligence. It begins by defining QRP, pi as a branch of Q** operator, determined by partition P and permutation pi. Proposition 3.2 is a fundamental result that provides insight into the structure of ** operator. Part A. states that Q** operator can be decomposed into a union of subspaces, each corresponding to different partitions of the set 1 M into R subsets. This decomposition is crucial for understanding the geometric properties of Q** operator. Part B asserts that any two subspaces QR and QR are either identical or have no intersection, implying they form a partition of Q** operator. QR can be expressed as a union of QRP, pi over all possible partitions P and permutations pi. Part C demonstrates that QRP is an affine subspace of dimension Mr. plus erm0 D, revealing the geometric structure of QRP. The proposition also proves that for any theta** operator in QRP, there exists a neighborhood U such that U intersection QRP equals U intersection QRP, indicating QRP is a locally closed subset of QR. The Hausdorff dimension of QR is Mr. plus erm0 D, based on established properties. The proof of proposition 3.2 a begins by considering the general theta** operator in Q** operator and its corresponding function g, theta** operator x, f** operator x. It is then shown that the cardinality of the set W** operator 1, W** operator m, must be at least M0, and that theta** operator must belong to QRR, for some M0 is less than or equal to R, is less than or equal to M. Consequently, Q** operator can be represented as a union of QRR over all possible R. This section provides a detailed analysis of the fragmentation and stratification of Q** operator, shedding light on its geometric and topological properties, which are essential for understanding the behavior of the risk function R near Q** operator and the optimization problem in question. The research paper discusses the development of a novel algorithm for optimizing complex systems. It introduces a new mathematical framework that leverages the concept of nonlinear dynamics to improve system performance. The algorithm, dubbed Dyna-opt, is designed to adapt to changing system conditions by dynamically adjusting parameters. This approach has been shown to significantly enhance system efficiency and resilience. The paper also presents detailed analyses and simulations demonstrating the efficacy of Dyna-opt in various scenarios. The branch intersection lemma is a pivotal component in the analysis of neural network models, as it provides insights into their structure and properties. This lemma states that under certain assumptions, if two partitions P and P, of a set 1 M, have a specific relationship with a permutation pi, then the intersection of their corresponding quotient spaces QR, P, and QR, P, is contained within a specific subset of the quotient space, SRK, for some k. The proof of this lemma involves considering sequences of points in the quotient spaces QR, P, and QR, P, that converge to a common limit, theta. By analyzing these sequences and their relationship with the partitions P and P, the authors demonstrate that theta must belong to a specific subset of the quotient space, SRK, which is determined by the number of distinct indices in the intersection of the partitions. An example is provided to illustrate this concept, where a 3-neuron model is used to approximate a 1-neuron target function. This example highlights different branches of the quotient space, each with varying Hausdorff dimensions. These branches correspond to different configurations of the neural network's weights and biases, and their dimensions reflect the complexity and expressiveness of the model. The significance of this lemma lies in its ability to provide insights into the geometry and topological properties of neural networks, particularly in terms of how different partitions and permutations can affect the model's behavior and performance. By understanding these relationships, researchers can better design and optimize neural networks for various applications. The geometric relationships between various branches of QRPs are examined, with a focus on their intersections and closures. Each branch's closure is an affine subspace of R3, D+1, resulting in complex structures at their intersections. Figure 4 illustrates the intersection of Q3, 0, 1, 2, 3, Q2, 0, 1, 3, and Q1, 0, 3, from the W space perspective. demonstrating how these branches intersect and overlap. The right side of the figure shows the intersection of Q2Ps, consisting of three geometrically identical branches with the same R but different permutations, and their intersections are identical up to permutation. Figure 5 provides a complementary view from the space perspective, showcasing the intersection of Q3, 0, 1, 2, 3, Q2, 0, 1, 3, and Q1, 0, 3, which further emphasizes the intricate geometry and relationships between these branches. The concept of a deficient number is introduced, defined as a partition P equals Q0, QR of 1, M, with a deficient number L. L is greater than or equal to 0. If there are precisely T1, TL element of M0 plus 1, R, such that QTJ1 equals 1 for all 1 is less than or equal to J is less than or equal to L. Notably, if P has a deficient number L greater than 0 and theta asterisk operator equals a asterisk operator K, W asterisk operator K, RK equals one element of QRP, then there are exactly L distinct W asterisk operator Ks whose corresponding to asterisk operator K equals 0. The deficient number, combined with separating inputs, provides valuable information about the rank of the Hessian of R at QRP, which will be explored in subsequent sections. Morse-Bott functions are a crucial concept in understanding the local convergence of gradient flow near each branch of Q asterisk operator. These functions, denoted as f, r, d plus 1, m right pointing arrow r, have a non-empty submanifold M subset equal nabla f, 1, 0, within R, D plus 1, M. The normal bundle of M is represented by NM right pointing arrow M, and for any point P element of M, the restriction of Hess P to NXM times NXM right pointing arrow R is referred to as Hess MF P. A manifold M is considered a non-degenerate critical manifold of F if Hess MF P is non-degenerate for each P element of M, and such a function F is called Morse-Bott at M, if there exists a neighborhood of M where nabla f, 1, 0, equals M. Examples of Morse-Bott functions include f, x, y, equals x n, with n equals 2, 3, 4, and any analytic function whose set of critical points are submanifolds and whose Hessian are non-degenerate at the normal spaces of it. In the context of neural networks, a specific example of a Morse-Bott function is the linear regression model with L2 loss. The Hessian of this function is a constant matrix-valued function, which implies that nabla r, 1, 0, is a union of affine spaces that are all orthogonal to Kerr, Hess R. This page also includes a lemma that proves the function r, defined as the sum of squared differences between predictions and actual values, is a Morse-Bott function. This lemma is essential for understanding the behavior of gradient flow in neural networks and its implications for optimization algorithms. Analyzing the properties of the loss function r, theta, under the assumption sigma, x, equals x and m equals n equals 1, the authors demonstrate that the gradient nabla r, theta, vanishes if and only if theta belongs to the codimension 1 submanifold M of Rho plus 1. This submanifold M is characterized by a constant rank 1 Hessian, indicating non-degeneracy. This setup is particularly relevant to the study of Morse-Bott properties of the loss function in the context of two-layer neural networks. To illustrate this concept, the authors consider the function f, x, y, equals x2 minus y2, showcasing its zero set and the non-degeneracy of its Hessian along the normal bundles. This analysis is crucial for understanding the behavior of the loss function near imperfect global minima and for determining sample size thresholds for branches to be separated from these minima. The author's findings have significant implications for understanding the properties of the loss function, particularly in the context of neural networks. By characterizing the submanifold M and the non-degeneracy of the Hessian, the authors provide a framework for analyzing the loss function's behavior near critical points, which is essential for optimizing neural network performance. In the overparametrized case, under assumptions 2.1 and 2.2, lemma 4.2 presents three key results regarding the separation of Q** operator. These results consider a set of separating inputs, Xi, d plus 1, mi equals 1 for an arbitrary choice of distinct Wm0. Wm element of road, weak, m0k equals 1. The function r, theta, is defined as the sum of squared differences between g, theta, xi, and f asterisk operator, xi, over the inputs. Result A states that when n is less than or equal to d plus 1, m0, any theta asterisk operator element of q asterisk operator has an open neighborhood U such that R is Morse-Bott at U intersection R minus 1, 0. This implies that the Hessian of R at any theta asterisk operator element of U intersection R minus 1, 0 is non-degenerate. This result relies on proposition 3.2, which states that Q asterisk operator equals SMR equals M0 SP, pi QRP, pi. This implies that there exist K1, Km0 element of 1, m, such that a asterisk operator Kt does not equal 0 and W asterisk operator Kt equals Wt for all 1 is less than or equal to T is less than or equal to M0. The separating inputs, xi, d plus 1, mi equals 1 are used to show that for any 1 is less than or equal to I is less than or equal to n. Nabla theta. G. Theta asterisk operator. Xi, f asterisk operator, xi, does not equal 0, and thus the Hessian of g, theta asterisk operator, xi, f asterisk operator, xi, squared has rank 1. This implies that the set, high, theta asterisk operator, ni equals 1 is linearly independent, and by continuity, there exists an open neighborhood U of theta asterisk operator such that, high, theta, ni equals 1 is linearly independent for any theta in U. Result B considers a partition P with deficient number L and states that when n is less than or equal to R plus RL, D, there exists an open U subset equal road plus 1 meter such that R is Morse-Bott at U intersection R minus 1, 0. Furthermore, when n is greater than or equal to R plus M0 R, D, up to an arbitrarily small perturbation of samples, there exists an open U subset equal road plus 1 meter such that R is Morse-Bott at U intersection R minus 1, 0, if and only if U intersection QRP subset equal U intersection R minus 1, 0. Result C states that when R less than M plus M0, 2, R is not Morse-Bott at U intersection QRP. However, when R is greater than or equal to M plus M0, 2, the samples in U can be chosen such that R becomes Morse-Bott at U intersection QRP if and only if L equals 2 RMM0. The codimension of the manifold M is demonstrated to be n. When theta asterisk operator element of U intersection R minus 1, 0, each high theta asterisk operator is an eigenvector for the only non-zero eigenvalue of Hess, G, theta asterisk operator, xi, minus f asterisk operator, xi, squared, and the linear independence of high theta asterisk operator, S yields rank, Hess R, theta asterisk operator, equals n, implying that Hess MR, theta asterisk operator, is non-degenerate for each theta asterisk operator element of M. Thus, R is Morse-Bott at M equals U intersection R minus 1, 0. Assuming n is less than or equal to R plus R minus L, D, it is shown that for theta asterisk operator element of QRP, rank, Hess R, theta asterisk operator, equals n. Specifically, theta equals a asterisk operator K. W asterisk operator K, Mk equals 1 is chosen such that W asterisk operator Qt equals WQt for all 1 is less than or equal to T is less than or equal to M. And for any 1 is less than or equal to T is less than or equal to M minus L, there is some Kt element of Qt minus 1 plus 1, Qt, with a asterisk operator Kt does not equal 0. By the hypothesis on the separating inputs, it is shown that the rank of a certain matrix is n. This implies that rank Hess R, theta asterisk operator, equals n, and by continuity, there exists an open neighborhood U subset equal R, D plus 1, M such that rank Hess R, theta, is greater than or equal to n for all theta in U. The intersection M equals U intersection R minus 1, 0, is a transverse intersection of n submanifolds in R, D plus 1, M, and hence a submanifold having codimension n. It follows that for any theta asterisk operator element of M, Hess MR, theta asterisk operator is non-degenerate, and R is Morse-Bott at U intersection R minus 1, 0. Finally, assuming n is greater than or equal to R plus M0 minus R, D, it is shown that by perturbing x1, x arbitrarily small, a Q asterisk operator, S, can be contained in a countable, possibly finite, union of analytic submanifolds M1, M2, of R, D plus 1, M with codimension n. The function R, defined as the sum of squared differences between a neural network's output and a target function f over a set of n input points, exhibits distinct properties. The core result, presented in Lemma 4.2, comprises three key components. Firstly, R is Morse-Bott at Q, a critical point. Secondly, for R exceeding M plus M0, 2 in L equal to 2Rm M0, R is also Morse-Bott at QRP, a set of points with specific properties. Thirdly, R fails to be Morse-Bott at QRP when R is less than M plus M0, 2 or L exceeds 2Rm M0. Furthermore, remark 4.1 strengthens these results, establishing that R is Morse-Bott at the intersection of an open set U in R, D plus 1, M and the preimage of 0 under R, denoted by R1, 0, which contains Q. Notably, for cases B and C, the open set U can be chosen such that its intersection with QRP forms a dense subset of QRP. In the overparameterized regime, the geometry of QRP, pi is equivalent to that of QRP. A crucial finding is that there exists an open set U in ROAD plus 1 meter such that U intersects R caret 1, 0 is equal to U intersect QRP, but not for QRP, as demonstrated in Figure 7. The authors then present Lemma 4.3, which addresses the separation of Q asterisk operator in the underparameterized case. This lemma consists of two parts. Part A states that for any natural number n in open set O containing Q asterisk operator, there exists a finite collection of samples such that B, 0, n, intersect R caret 1, 0, is contained in O. Part B claims that for any collection of inputs, xi, ni equals 1 with n greater than D plus 1, m and any epsilon greater than 0. We can perturb each xi with no more than epsilon distance to obtain a new collection of inputs, x, I, ni equals 1, such that R caret 1, 0, equals Q asterisk operator. The proof of Lemma 4.3 is also provided. In Part A, the authors fix theta in B, 0, n, but not in Q asterisk operator, and show that the set X in ROAD G, theta, X, equals F, X, has lambda D measure 0. They then find X theta such that G, theta, X theta, is not equal to F, X theta, and by continuity, G, theta, X theta, is not equal to F, X theta, on an open subset B theta of B, 0, n. By compactness, they can find theta 1, theta n in B, 0, n, O such that B, 0, n, O is contained in the union of B theta I. They said R equals Pni equals 1, G, theta, X theta I, F, X theta I, squared, and show that B, 0, n, intersect R caret 1, 0, is contained in O. In Part B, the authors let East equals ROAD plus 1 meter Q asterisk operator, and show that for any theta in E, the function, theta, x, rightwards arrow from bar G, theta, x, f, x, satisfies that for any theta in E, x rightwards arrow from bar G, theta, x, f, x, is not constant 0. By corollary 3.4, for almost all inputs, x, I, ni equals 1 and R, theta, equals Pni equals 1, G, theta, x, I, f asterisk operator, x, I, squared. They have E intersect R caret 1, 0, is empty, or R caret 1, 0, equals Q asterisk operator. In the context of target function estimation, uniqueness is not guaranteed given samples, xi, yi, ni equals 1. However, proposition 4.1 ensures that, under assumptions 2.1 and 2.2, a dense set of separating inputs leads to a unique target function f** operator at overparameterization. This means that, in general, only one fixed target function needs to be considered. Proposition 4.1 states that, for almost all separating inputs, x, I, ni equals 1, the unique global minimum of the function r is theta equals ac weak m0k equals 1, which corresponds to the unique target function f** operator. The proof involves perturbing the inputs xi arbitrarily small using lemma 4.2 to obtain x, I, ni equals 1, ensuring theta becomes the unique global minimum. The paper then explores the dynamics of gradient flow near q** operator, leveraging Lojosevich-type inequalities to demonstrate the convergence of gradient flow near the critical points of a real analytic function f. Theorems 5.1 and 5.2, derived from p phi and p absol, respectively, show that for an analytic function, any gradient flow near a local minimum converges. Theorem 5.1 states that for any critical point p of f, there exists a neighborhood U of P and constants C greater than 0, microelement of 1/2, 1, such that nabla f, Q, is greater than or equal to C, f, Q, f, P, micro for any Q in U. Theorem 5.2 rephrases Theorem 2.2 in P absol, stating that any non-constant gradient flow with initial value x0 element of U converges to f, P, with a convergence rate 0 less than beta less than 1 depending only on P. The proof commences by invoking Theorem 2.2 from P absol to establish the existence of a neighborhood U around P, ensuring that any gradient flow gamma originating from U satisfies a bound on its length. This is achieved through the monotonic convergence theorem, which guarantees the boundedness of the length of gamma. The neighborhood U can be chosen such that f, Q, is greater than or equal to f, P, for Q in U, and by Theorem 5.1, this implies nabla f, Q, equals 0 is possible only for Q in f-1, f, P. The proof then proceeds to demonstrate that if f is non-negative and f-1, 0, is non-empty, any gradient flow with initial value in U converges to f-1, 0. This result is established by leveraging the properties of the function f and its hypotheses. The converse result is also shown, stating that if f is analytic near n, any point in n is the limit of a gradient flow. This involves proving that for each point x** operator in f-1, 0, there exists a non-constant gradient flow converging to x** operator. The proof utilizes sequences of gradient flows and their limits to establish this, leveraging the hypotheses on the function f and its properties. In the realm of optimization theory, a significant focus lies on the convergence properties of gradient flows for specific loss functions. One such function, R, is shown to be analytic under certain conditions, which has profound implications for its behavior in dynamical systems. Of particular interest is the behavior of gradient flows near a fixed point QRP, pi, given that QRP, pi is separated. This necessitates the application of a parameterized version of center manifold theory to the dynamical system, allowing for an examination of the convergence rate and limiting direction of the gradient flow. To support these claims, detailed mathematical proofs and equations are employed, including the use of Gronwall's inequality and the application of a boundedness result. These tools provide insight into the stability and convergence of the gradient flow, shedding light on the role of the fixed point in the system's behavior. The discussion is highly technical, requiring a strong background in differential equations, dynamical systems, and optimization theory. It highlights the importance of understanding the properties of gradient flows and their role in optimizing complex systems. In the context of systems behavior under specific conditions, the maps f, g, and m exhibit a quadratic relationship with x and y as they approach 0. This is denoted as O, x squared plus y squared, indicating that these functions can be estimated to have a magnitude proportional to the sum of the squares of x and y. The discussion then turns to a simplified system, which serves as a foundation for understanding the convergence of solutions. A key lemma is presented, stating that if the system converges to a point, 0, 0, z, with z in up, then under certain conditions, y, t, decreases to 0 at an exponential rate. This exponential decay is a significant finding, as it suggests that the system's behavior can be characterized by a rapid convergence towards equilibrium. The proof of this lemma involves a detailed analysis of the components of y, t, and z, t, over time. It demonstrates that y, t, converges to 0 at a rate proportional to x, t, squared, further reinforcing the quadratic nature of the system's behavior. This insight provides valuable information about the stability and long-term behavior of such systems, which is crucial for researchers seeking to understand and predict their dynamics. When time t exceeds the threshold t, the difference between z, t, and z is bounded by a constant z infinity, meaning z, t, z is less than or equal to z infinity. Additionally, the integral of the absolute value of the derivative of z with respect to zeta, from 0 to t, is bounded by czsx, where cz is a constant. This results in the inequality, y, t, squared is less than or equal to cz's, lambda squared, y, t, squared, implying that z, t, z, equals o, y, t, squared, as t approaches infinity. Assuming h, z, is diagonal with eigenvalues lambda, lambda s, and lambda is half of the maximum eigenvalue, it is shown that g, x, y, z, is less than or equal to psi, x, squared plus, y, squared, for some constant psi. The quotient q, t, is defined as y, t, squared, x, t, to the power of 4 for t is greater than or equal to 0, where x, t, is non-zero. Under the assumption that the limit of q, t, as t approaches infinity is finite, a contradiction is derived. Specifically, a sequence, Tn, is constructed such that y, Tn, equals k, x, Tn, squared, and the derivative of q at Tn is non-negative. Using the expression for the derivative of q, which involves the inner product of y and h, z, y, and the bound on g, it is shown that the derivative of q is less than or equal to 2k, lambda k plus 2 psi, o, x, Tn. Since lambda is negative, this leads to a contradiction, as the derivative of q is non-negative. In systems with a positive damping coefficient, c greater than 0, understanding the relationship between the difference in position from equilibrium, z, t, minus z asterisk operator, and the magnitude of the displacement, x, t, is crucial. This relationship becomes increasingly important as c greater than 0, due to the lack of a clear estimate. A key lemma is presented, which states that for such systems, if a solution curve converges to an equilibrium, then the magnitude of the velocity, y, t, decreases at least as fast as the square of the displacement, x, t, plus an exponential term. This result is proven by analyzing the center manifold of the equation and demonstrating that the difference between the actual solution and the center manifold decreases exponentially. The implications of this finding are significant for the stability of the system and the behavior of the solution curves, providing valuable insights into the dynamics of these complex systems. The function h, x, z, exhibits twice continuous differentiability in both x and z. Its approximation theory reveals that the partial derivative hz, x, is of order x squared. A crucial bound on the behavior of y, t, in terms of x, t, and z, t, is established using the largest eigenvalue of h, z. Notably, if the trajectory of gamma has a tail length of omega, e micro t, for some micro less than lambda, then y, t, converges to o, x, t, squared, as t approaches infinity. This is achieved by bounding the integral of x, s, squared plus y, s, squared, leveraging the approximation theory of the center manifold. The limiting direction of the solution curve for system 13, with c greater than 0, viewed from the z-plane, is biased towards the y direction and non-degenerate. This concept is further explored through the introduction of subspaces Vs, Vp, and Vc, along with linear operators πs, πc, and pi p for projections onto these subspaces. The decomposition R, d plus 1, m equals vc circled plus v's circled plus vp allows any element theta element of R, d plus 1, m to be represented as x, y, z. An example illustrates the Hess R, x, y, z matrix for a given function R, x, y, z equals x2 plus y4 plus 0z. The training dynamics of R are then investigated, focusing on the properties of the gradient flows near r-1, 0, particularly when it is near q** operator. The convergence of gradient flow is discussed in Theorem 5.3, detailing conditions for convergence and the behavior of pi p, gamma, t, minus theta * operator, and pi s, gamma, t, minus theta * operator, as t plus infinity. This refined version maintains the technical accuracy and depth of the original content while condensing it into a concise, direct form suitable for voiceover narration. The authors present two main results regarding the convergence rates of gradient flows. First, they show that if n is greater than or equal to m plus m0r, d and m0 plus m2 is less than or equal to r is less than or equal to m, then for almost all theta * operator element of QRP, the flow converges at a linear rate with pi s, gamma, t, theta * operator, equals O, pi c, gamma, t, theta * operator, squared, as t right pointing arrow plus infinity. This is proven by assuming a coordinate transformation and applying remark 5.1 and lemma 5.1, a. The second result states that if m0 is less than or equal to r less than m plus m0 or the deficient number L of p satisfies L less than 2rm m0, then for almost all theta * operator element of QRP, the flow also converges at a linear rate with pi s, gamma, t, theta * operator, equals O, pi c, gamma, t, theta * operator, squared, as t right pointing arrow plus infinity. This is proven by defining S as the maximum of rank Hess R, theta * operator, for theta * operator element of QRP and applying a coordinate transformation tau, theta * operator. The authors also note that when R element of m0, m, and n is greater than or equal to r plus m0r, d, the rank of Hess R is constant on QRP, and any gradient flow sufficiently close to R, 0, converges to R, 0. Theorem 5.2. Corollary 5.1 addresses the convergence of loss, with specific conditions on m0, r, and n. For almost all theta * operator in QRP, the result holds when n is greater than or equal to m plus m0r, d and m0 plus m2 is less than or equal to r is less than or equal to m. The corollary presents two cases based on the deficient number L. In the first case, where L less than 2rm m0, it is shown that r, gamma, t, right pointing arrow r, theta * operator, equals 0 at a linear rate as t right pointing arrow plus infinity. In the second case, when n is less than or equal to d plus 1, m0, the same result holds for any theta * operator in R1, 0, sufficiently close to q** operator. The proof involves utilizing the local Lipschitz property of R and Theorem 5.3 to demonstrate that R, gamma, t, right pointing arrow 0 at a linear rate. A second part of the corollary discusses the case where L less than 2rm m0, proving that R, gamma, t, equals O, gamma, t, theta * operator, 4 plus e beta t, for some beta greater than 0. This refined version maintains the technical accuracy and depth of the original content while condensing it into a concise and clear summary suitable for voiceover narration. The convergence rates of gradient flows and loss near different branches are discussed in this section, with a focus on the stability of points in q** operator under perturbations. A summary of Theorem 5.3 and Corollary 5.1 is provided, highlighting the convergence rates for gradient flows and loss. The concept of recovery stability is then introduced, defined as the ability of a point theta asterisk operator to remain stable under perturbations. Theorem 5.4 explains the recovery stability of points in Q asterisk operator based on the number of samples n. The proof of this theorem is outlined, demonstrating the equivalence of recovery stability and the existence of a neighborhood with no points in R-1, 0, Q asterisk operator. The recovery stability of points in Q asterisk operator is discussed, where any 2 points in Q asterisk operator represent the same model F asterisk operator. It is shown that theta asterisk operator is recovery stable, implying G, theta asterisk operator, X, equals F asterisk operator, X, equals G, lim T right pointing arrow infinity sign GTH0, T, X, for all X element of road. The relationship between sample size and recovery stability of points in Q asterisk operator is then explored. Table 2 illustrates the sample size thresholds that determine the recovery stability of points in branches of Q asterisk operator. When the sample size n is less than or equal to d plus 1, m0, no point in Q asterisk operator is recovery stable. However, as the sample size increases, points in certain branches become recovery stable. Specifically, when n is greater than or equal to r plus m0r, d. Almost all points in branches qr plus 1, qm are recovery stable. Moreover, when n greater than d plus 1, m, any point in Q asterisk operator is recovery stable. The paper concludes by summarizing the key findings on the geometry and dynamics of the loss landscape for two-layer neural networks. The global minima with zero generalization error are shown to be partitioned into distinct branches that become geometrically separated from other global minima as the sample size increases. The sample size thresholds for this separation are identified, and it is demonstrated that the loss function R is Morse-Bott at almost all points in certain branches, ensuring non-degenerate Hessians along their normal bundles. Gradient flows sufficiently close to the global minima are shown to converge to points within these minima, with linear convergence near Morse-Bott branches and sublinear convergence near others. The concept of recovery stability is introduced, and it is shown that almost all points in certain branches are recovery stable when the sample size is large enough. The results provide a detailed understanding of the loss landscape and training dynamics of two-layer neural networks, explaining their ability to find well-generalizing solutions even in the overparameterized regime. This work lays a foundation for further studies on the global recovery capabilities and generalization performance of neural networks. The paper concludes by highlighting several potential avenues for future research. One direction involves extending the analysis to deeper neural networks with more than 2 layers to understand the increased complexity in the loss landscape. Another area of interest is exploring how different activation functions, initialization schemes, and regularization techniques impact generalization capabilities, training dynamics, and performance. Empirical studies are needed to validate theoretical findings and explore practical implications. Research on global recovery and generalization could provide a comprehensive understanding of neural networks' ability to generalize from a global perspective. The paper acknowledges the support received from various grants, including the National Key R&D Program of China, the National Natural Science Foundation of China, the Shanghai Municipal Science and Technology Key Project, the Leyang Laboratory, and the Shanghai Municipal of Science and Technology Major Project. The mathematical foundations of neural networks are rooted in geometry and optimization landscapes. Convergence of descent methods for analytic cost functions is crucial for understanding optimization in machine learning. References such as Absal's work on the convergence of iterates of descent methods and Breiman's reflections on the importance of rigorous peer review provide a solid foundation. Center manifold theory, as detailed in Carr's book, has implications for understanding complex system behavior, including neural networks. Morse theory, explored in Cohen et al.'s lecture notes, studies critical points of smooth functions on manifolds. Cooper's paper sheds light on the global minima of overparameterized neural networks, while E et al.'s review offers a broad overview of mathematical understanding and the unknowns in neural network-based machine learning. Fian's research addresses singularities and geometric proofs of the Lojasiewicz inequality, a fundamental result in real analysis. Fukumizu and Amari's study examines local minima and plateaus in hierarchical structures, and Krantz and Park's primer on real analytic functions serves as a foundational text. Li's introduction to smooth manifolds provides a comprehensive treatment of differential geometry, relevant to neural network landscapes. Simcik et al.'s paper investigates the geometry of the loss landscape, focusing on symmetry and invariances. Sun et al.'s chapter emphasizes the global landscape of neural networks and the role of nonconvexity in optimization. Venturi et al.'s research explores spurious valleys in one-hidden-layer neural networks, highlighting the importance of considering the optimization landscape. Zhang et al.'s paper emphasizes the need for rethinking generalization in deep learning. This reference list spans topics from optimization in geometry to differential topology and non-convex optimization, providing a comprehensive foundation for researchers.